And we start chapter 2, which is called The Rise of Astronomy. It's very much, of course, related to chapter 1. Remember, chapter 1 is basically the cycles of the sky, where what people could see without telescopes. This is actually going to go back to that, and then also include the time about 400 years ago when humans started using telescopes as well. All right, so let's get right into it. This is what's called an orrery. It's a model of the solar system. You notice I can tell right away that this is older. This is less than 400 years old, certainly, because Saturn has rings right here. And also, some of these planets have moons. Humans didn't know about that until the invention of the telescope. This particular picture is this completely mechanical. You physically turn this thing, and you were trying to reproduce the motions of the planets around the sun, which, of course, not everybody, um, even just a few hundred years ago, believed that all the planets travel around the sun. That's kind of what this part of what this story is about. So we're going to start with the Greek astronomers. Of course, there were others, but it's a good starting point for our story here. Is the Greeks, because they made lots of observations. You might recall in the last chapter they were talking about um, the model of that we still use today called the celestial sphere. So the Greeks were extremely important, and of course other cultures were important about looking at the night sky. The thing about the Greeks is they wrote stuff down, and we can still read that stuff. I mean, there's still humans that have been taught to read Greek, and so that's still something that we can study. All right, so at any rate, this is a good starting point. Um, so this is over 2,500 years old. Um, Remember, they're only using their eyes to look at the sky. They're using logic. They were very fond of mathematics. Um, and the link between mathematics and and the descriptions of the universe, um, really starts with the Greeks. Uh, all right, and then they investigated, and then tried to figure things out. I mean, they weren't always really good at doing this. The what we would call the modern scientific method certainly was millennia, millennia into the future. In fact, that doesn't come around until about 400 years ago, which actually corresponded um, with the telescope. Right around the time of the telescope is the time when the modern scientific method first takes place. All right, so going back, roughly 2,500 years ago, there was this guy Pythagoras. Of course, you've probably heard of Pythagoras' theorem: a squared plus b squared equals c squared, regarding right triangles. But he also was one of these individuals who thought about other things, um, not for any really good reason other than he felt that circles were perfect, and so he thought that the Earth was a sphere, and he wrote that down, of course, um, and it was just really just thinking about the shape itself. It wasn't, this was more of a mystical reason than anything else. He was a mathematician certainly, but he was also a mystic at the same time. Um, all right, and by the way, this was the last time humans were his little cult, that formula that everybody knows nowadays. That was actually a well hidden secret in his own time, and he would share this with other members of the quote cult, the mathematical cult, and you were subject to death if you shared that information. Thank goodness that information did eventually get shared with the rest of the human race as time went on. And then we move forward about 200 years to the time of Aristotle. Um, so now this is a very scientific thing. I mean, some of the stuff that Aristotle did was not considered would not be considered scientific at all. But this particular observation is very scientific. If we noticed that during a lunar eclipse, right, when the moon is passing through the Earth's shadow that we mentioned in the last chapter, he noticed that as that was happening, the shadow was round, and he concluded he realized, hey, that there's only one reason for that, and that's because the Earth is round. I mean, you're not going to see this big round shadow on the surface of the moon. Remember, a new moon, or sorry, a lunar eclipse is only going to happen during a full moon, right? As the moon passes through the Earth's shadow, and so you see that curve of the shadow, and you realize that um, it is the Earth that's round. All right, let's move on to the next one. All right, so that was one observation about the roundness of the Earth. Another thing that this is important because he wrote these things down. Aristotle also noticed, and I'm sure other people noticed this as well, is that if you're, let's say you're, on a port city in the northern Mediterranean Sea, and you watch a ship take off and it's heading south, more than likely that would be a Greek, that would be a ship leaving Greece. At any rate, if you watch the ship as it sails south, you notice that the very last thing that you see would be the top of the ship. All right. Now you'd have to watch as the ship gets further and further and further from you, but you would slowly the hull of the ship would disappear over the horizon, and then the last thing that you see are the sails, or the top of the sails. Maybe there's even a flag at the top, and you see that flag dip down below the horizon. And now the only way that that's going to happen, of course, is if the Earth is round. All right, so that's just one example. It doesn't, you don't have to be moving to the south. I'm just using that for, you just imagine you're looking from Greece. All right, so anyhow, because that's kind of where Aristotle lived. All right, and then let's see. So you can also, oops, did I skip? I skipped. Okay, I guess I skipped here we go. All right. So I already did that one. So sorry, I didn't mean to go that far back. All right. And so that is what Aristotle had done. There was a guy that was lived, about 100 years or so after Aristotle, and his name was Aristarchus. His name is he's almost lost to history, but of course the fortunate thing is that he wrote some stuff down. And Aristarchus actually had several things right, and he he was actually his observations led to conclusions that were much better than many of Aristotle's conclusions. One of Aristarchus's conclusions was, from his observations, was that that the moon was much closer than the sun. All right, so he realized that. And so he also estimated the size and the distance using geometry, and these lunar eclipses and solar eclipses. He estimated what the size of the moon was compared to the sun. Now, he didn't get really good numbers or anything like that, but for the very first time in human history, Aristarchus actually, estimated the size of the moon and the size of the sun. I mean, that was a big deal, right? That was, for the very first time, we had estimations on the size. Again, even though those numbers were actually wrong. All right, and so one of the things that we're going to cover, and this is another thing that he did. He used this idea of angular size. So let me show you the equation. That this is just a picture of where this comes from. And so this is actually, I'm going, in the formula sheet, I've modified this. The L is the length of an object. So that's the actual, like the width of the moon, for example. If that's L, and the distance to the moon, that's what D is, then L and D are related to the angular size of the moon, right? So the angular size is what we call alpha here. Now, in the formula sheet that I use, I always take the 2 and the 300. The 2, of course, goes into the 360, and so it's L times pi over 180 times D times alpha, where D is the distance between what you're looking at and you, and then L is the actual size of it. So L would be for example, for the moon, that would be a good example. L would be the size of the moon, and so alpha, for example, would be something you can observe on Earth. All right, so that's this formula. Oh, and I'll start with this in the next video.